Okay, how about you now? Okay, yeah, good. Okay, so thanks for coming. So I'm currently a faculty member at Imperial College London in the UK, and also recently I started just splitting my time also at Nanyang Tech University in Singapore. So I actually affiliated with two universities, and I get PhD students on both sides. Okay, but most of the things that I'm going to talk about today will include tutorials on this very interesting topic, uncertainty in deep learning, as well as some works from my PhD students listed here. Okay. So, well, of course, nowadays we already know how amazing these language models are, right? But starting from the very beginning of language models, right, there is always this interesting question about hallucination of language models, okay? Right, so there has been a lot of debate in terms of like, oh, can we actually eliminate hallucination to what extent or what, right? So there is actually a very interesting blog post last year by OpenAI. Okay, you can still find that on their website, and they basically ask the question about why language model hallucinate. Or they have a lot of interesting discussion, but at the end of the day, here's the claim from their blog post. Okay, so hallucination cannot be eliminated, okay, because you cannot reach 100% accuracy, okay, unless you basically have the entire data set or infinite amount of data, okay. But it is not inevitable, right, because at least they claim that you can ask your language model to decide not to answer your question when they are somehow not sure whether the right answer, whether the answer they predicted is actually correct or not, right? So it says that because language models can abstain when uncertain, hallucinations are not inevitable. So this is their claim, okay? So you can see this interesting keyword uncertainty appears. So this basically says you need to find out a way to actually address uncertainty quantification in large language models. So here's the interesting question again, right? So nowadays, all these hypes tells you that AGI is coming. AGI is coming in the next 3 to 5 years. So maybe after we solve the AGI, uncertainty quantification will be solved by then. Okay, so from my perspective, this is actually not true, right? So you haven't actually talked about what you really mean by solving uncertainty quantification, right? And also in what scenarios, right? So can you actually perform uncertainty quantification for arbitrary covariance shift, basically any out of distribution data? Can you actually get any personalized guarantees? So let's say if you are a new user to the language model, right? So you've never used language model before, and you ask a very personalized question, okay, maybe a very private question, if you really want to ask for the language models. Can the language models answer to your very private question, especially when you haven't used language models before, actually gives guarantees? No. Okay, so can you actually use language models for reliable decision making? We will talk about what this reliability means in a second, right? So that it will be another question. And even more, right? So people are now interested in seeing whether you can use AIs to discover new knowledge. The question here is what kind of new knowledge, right? Is that a new knowledge based on interpolation of existing knowledge, or like knowledge of unknown unknowns? Basically, you actually don't know what kind of a new knowledge you want to discover, right? So when you have unknown unknowns, can you still get guarantees? Okay, so you can basically see there are a bunch of interesting questions about, well, whether uncertainty quantification will be solved by AGI, right? And in fact, well, I guess maybe can we make a little bit smaller for the screen? Yes, okay, no problem. So this is a joke I make, right? So in fact, if you talk with statisticians, basically, in my opinion, statistics is the science of quantifying uncertainty. Okay, so more or less, if you talk about this AGI solving uncertainty quantification, then statisticians will basically come and fight with you. Okay, so I've got some motivations, but what is uncertainty quantification, and especially how do you do uncertainty quantification in deep learning, right? So in today's lecture, we will talk about this topic in 3 parts. Okay, so first of all, I will talk about how Bayesian statisticians or Bayesian machine learning people actually tries to compute uncertainty for neural networks. Okay, and then afterwards, I will talk about another line of work, which is basically from frequentist statistics. So Bayesian statistics and frequentist statisticians sometimes fight with each other. Okay, but there exists other approaches from the frequentist perspective. Okay, so lastly, I will also show you some examples from my lab where will be something related to language models. Okay. Okay, so we can first go for Bayesian inference. Okay, so Bayesian inference is actually a very simple principle that based on this Bayes rule. Okay, so Bayes rule tells you that if I have some unknown quantities, unknown random variable theta that I want to estimate from data, then I should build essentially a prior distribution that represents my prior beliefs over the potential values for these latent variable theta, and then based on the likelihood, which means essentially how likely the parameter theta is under my data set, I will update my belief of the underlying value of this parameter theta by computing this posterior distribution here. Okay, so in particular, right, so for most of the Bayesian methods, including what we're going to discuss later, what we need to compute is this posterior distribution, okay, and which means you need to compute essentially this Bayes rule, so you have this integral that needs to solve. But in deep learning context, right, so we actually care about prediction. Okay, so what you can do with a Bayesian model here is once you have your posterior distribution over the latent variable theta, okay, that you're interested in, then you can compute essentially the prediction by marginalizing out all possible posterior kind of prediction examples. So here, I'm giving you one example that I pick this kind of integrand function f to be my likelihood, which basically says, okay, so if I have a data point x, I want to predict the outcome y, and my model has this parameter theta, okay, right? But I actually don't know what the ground truth model parameter is, right? But I only have a posterior belief. So I'm going to compute this integral by taking all possible solutions under my posterior belief and then produce the predictions. Okay, so let's just see how concretely speaking it applies to neural networks. Okay, so I guess this is maybe more familiar with you, right? So if you want to build a classifier that classifies between cats and dogs, right, then you build whatever interesting neural network architecture with neural network parameter theta, and then your likelihood here in this classification case becomes a Bernoulli distribution over your labels y given your input x. And the logic, right, in this softmax is produced by your neural network. So this is the usual classification setting. Well, this is just a very typical neural network setting, right? If this is a feed-forward neural network, then you will have multiple layers of this linear transform plus a bias, so that this parameter theta collects all of your neural network weights. Okay. Usually in deep learning, right, people actually do this cross-entropy optimization for classification, and this actually corresponds to something called maximum likelihood estimation, or MLE for short, in terms of getting the point estimate of the parameters. So in this probabilistic notation, right, so what you're doing here is you are summing over all the likelihood terms. So you can think about just the likelihood terms as the negative cross-entropy. Okay, and then you're trying to maximize your likelihood. Okay, once you get your parameters via this maximum likelihood procedure, then in test time you plug in your estimator theta star, and then this will produce your prediction. Okay, so this is the usual deep learning workflow, but in a Bayesian neural networks, at least the classical version of it, right? So what we would do here is, as I said before, Bayesian methods like to produce prior and posterior beliefs over the unknown parameters. So in this case, we are going to put on a prior distribution over your neural network weights. Okay, usually people use Gaussian prior, but there are other choices. So now, hypothetically speaking, you just imagine that you can apply Bayes rule. Just imagine that you can do that. So Bayes rule here just tells you that your posterior is proportional to the prior times likelihood. There is a dividing factor, but the dividing factor is a constant with respect to theta, so you don't need to worry about that for a moment. Okay, so assume you can compute this posterior, which we will talk about it extensively. Then in the Bayesian predictive inference, what you're going to do here is you just compute essentially the expectation over all possible predictions, where this expectation is under your posterior. Okay, so this is the concept, right? But of course, the major issue here for Bayesian methods, including Bayesian neural network, is actually the computation of this posterior. So what people actually do in practice is the following. So the exact posterior, in all of cases, they are intractable, okay, unless you use linear models and also Gaussian likelihood. So what people do instead is you find a easier distribution, what we call Q here, to approximate this posterior distribution somehow. We will talk about how this somehow means later, okay? And then once you've done this approximation, then in test time, we are going to compute this Monte Carlo approximation to the expectation here, right? So what this means here is you're going to sample from this Q distribution a few number of weights, for example, like K weights. And then for each of the weights, you compute the prediction here. So each of them will basically give you a probability of whether this image is likely to be a cat or this image is likely to be a dog. And then afterwards, you are going to ensemble all these sampled weights predictions together, and then compute this empirical average. So this will be the Monte Carlo estimation for the approximate predictive posterior that we are going to get. Okay, so effectively speaking, this feels like an ensemble method, but basically it is a random ensemble because you get samples from the Q distribution. Okay, so of course the question here is how do you actually get this approximate posterior, right? So maybe let's first say why it is important to make sure that this approximation is done correctly. So let's just to see how it works in practice, right? As I said, right? So you're going to sample a bunch of weights from your posterior, and then each of the weights is going to vote or going to provide a prediction for your image, and then they vote all together. So this is the ensemble method, right? So something that people have actually tried to do for neural networks is to test the robustness of their prediction. So for example, you can actually add in a small amount of noise, which is invisible to human eyes, but then the resulting image becomes adversarial to a single point estimate for the neural network. So this is something called adversarial examples that has been pretty classic kind of attacks to neural networks. Okay. But what you can do here with this Bayesian neural network here is you will have a random ensemble of neural networks, right, from your Q distribution. So each of the members will see this adversarial image. They will provide their own prediction, right? So, but hopefully, because of the diversity inside this plausible solution of Q theta, they will provide different predictions. So then it means that when you ensemble them together, you will either find out, let's say, the correct solution, or when they actually fail to find out the correct solutions, they can still disagree between each other, and disagreement here actually signals uncertainty in predictions. Okay, so this is the hope, but of course it depends on how you get this Q distribution. So imagine now you actually get a very bad Q distribution where this Q distribution is almost like a delta measure around a single point. So this means that all of your neural network samples from this Q distribution is going to be the same network. Okay, so you go back to the point estimate case again, and then your adversarial samples can easily fool your single, identical members in all these, say, ensembles. Okay, but of course, you also don't want this distribution to be too wide, right? If the distribution is way too wide, right? So it will cover a bunch of different neural networks where some of them might not be actually good, even in terms of clean in-distribution data. Right, so in this case, right, so even for the in-distribution data, maybe some of the networks already made mistakes, and then overall you also make mistakes. So I hope this example tells you that, okay, ultimately speaking, in this Bayesian neural network regime, the performance of the network really depends on how you get the Q distribution as the approximate posterior. Okay, so let's see how we actually perform approximate posterior finding in this Bayesian neural network. So basically, it contains 3 steps. So first, you need to define the distributional family of this Q distribution. So for example, you can use a Gaussian distribution, which is basically means you only need to know the mean as well as the diagonal of the covariance matrix. Well, you can also use like basically full covariance matrix, but remember here, theta is your neural network weights. Okay, so you have tens of millions or even say hundreds of millions, billions of weights. You don't want to do this covariance matrix. Okay, people sometimes also use low rank structure for your covariance matrix in order to save memory budget. Okay, so but also you can use non-Gaussian distributions. That won't be covered today. Okay, so you first choose a distribution, then it means that you don't need to fit this distribution to your posterior, and we are going to introduce variation inference as a popular approach to actually fit this Q distribution to the posterior. Okay, so the third thing here is, as I said, right, so once you've got the Q distribution, then you just perform prediction in test time with Monte Carlo approximations, which is explained before. Okay. So maybe let's just visualize what exactly is a mean field Gaussian distribution. So as I said, right, so it basically just says that I ignore the correlations in my covariance matrix because I don't want to parameterize a 100 million times 100 million matrix. No, okay. So instead, you only want the diagonal terms. So this essentially just tells you that I'm going to make the independence assumption for the, between the parameters within your big weight matrices. Putting that into these expressions, right? So it just tells you that I'm going to make these weights and the bias vectors independent. And then within a weight matrix, I'm also going to make their elements independent. Okay, so each of the elements will have their own mean and also their variance. So similarly for bias. So a little detail to say here is for Gaussian distributions, right? So your variance needs to be non-negative. And usually, if you want to do a good optimization, then you want your parameters to be unbounded. So usually what people do here is instead of parameterizing the variance directly, people will parameterize, for example, like the logarithm of the variance. Okay, so the variance is between 0 and infinity, and the logarithm of the variance is basically minus infinity to plus infinity. So this will actually make sure that your optimization is actually done in an unbounded space. Okay, so this is the first step. You can definitely choose other Q distributions, but for now we will work with the simplest one, which is mean field Gaussian. Okay, so the step 2 here is, of course, you want to get the Q distribution fitting. Okay, so this basically means we want to fit the distributional parameter phi with some objective function. So in the Gaussian case, right, phi will be essentially the mean and the log variance of your distribution. Okay, so we are going to actually use something called variational inference, which has the objective function that looks like this. Okay, so how it works is the following. So ultimately speaking, it is actually trying to minimize the KL divergence from your variational distribution to your true posterior. So let's see how it works. Okay, so first of all, this is the definition of the KL divergence. Okay, so if you haven't heard about KL divergence before, you just need to think about that a cross entropy loss is effectively speaking the KL divergence between from your data distribution to your model distribution, removing the constant. Okay, so but in this detail, right? So the KL divergence from Q distribution to some distribution P basically says you need to first compute the density ratio between Q and P, and then compute the integral of this density ratio under the distribution Q. Okay, so this naturally tells you that the KL divergence is not symmetric. If you swap Q and P, this will become a different expression, and the computation method will become completely different. So it is important that we are using KLQP. Okay. So another good property here is that KL divergence is a proper kind of divergence metric, which basically means KL is 0 if and only if P equals to Q. Okay, so this justifies KL as a valid metric to minimize, as to fit a Q distribution to your target distribution posterior. Okay, so as I said, right, so variational inference tries to approximate the posterior distribution P of theta given your data set D, okay, via minimizing the KL divergence from Q to the posterior. So let's just plug in the these two distribution in to the KL definition, right? Okay, so something that I'm going to rewrite a bit, which will be easier to understand later, okay, is I'm going to essentially swap the ordering of this Q and P here in the log density ratio, and then remember that log of a product equals to sum of logs. Okay, so effectively this is what I'm doing the first step. So you're computing the log density ratio between essentially the posterior and the Q distribution under the Q distribution expectation. Okay, so the second step here is just plug in Bayes rule. Okay, so this is just by definition of your posterior. Now, notice that the thing you want to optimize here is actually the Q distribution. So the posterior is provided by your model that is intrainable, but you want to approximate. So that is a fixed target that you don't want to touch. You only want to optimize Q. So now we are going to start, pulling out terms that are independent with Q. Okay, again, log of product equals to sum of logs. Okay, so this justifies why you can put this log of 1 over P D outside into this minus log PD. Okay, and then as I said, right, we want to pull out the things that are constant with respect to Q. So we are just pulling out this log PD term. Okay, so at the end of the day, we have rewritten the KL divergence. Okay, in terms of two terms. One term is called model evidence that is also very useful in the Bayesian statistics literature, but it is not the topic of today, right? The other term is actually related to the objective that we want to optimize. Okay, so this is just to make sure that it is clear, right? So I just repeat what I just written here, right? And then if you want to minimize the KL divergence with respect to the Q distribution, then you can also basically just maximize this equivalent objective because this log PD does not depend on Q. Okay, and in fact, if you think about the things that are difficult to compute in your posterior distribution, it is actually this log PD. Okay, because by definition, let me just go back, right? So by definition, so data here is your D, right? By definition, your log PD needs to solve a integral problem. Okay, and that is very difficult. We don't want to solve this integration problem. But now we don't need to solve this integration problem. Instead, we just optimize this objective. Okay, pictorially speaking, what you can see is this kind of a picture. The things that we want to minimize is basically the KL divergence from the Q distribution to the exact posterior, right? Which means you want to reduce the gap between the elbow and also the log PD, the log marginal likelihood. Okay, so reducing the gap, you can do two things, right? One, just directly reduce the gap, but another thing is you just push up the lower bound. Because your upper bound here, basically the log PD does not change, Okay, so there is no way to say that you push up the lower bound and then you also push up the log PD, at least in this basic neural network setup. So it means that pushing up the elbow by maximizing the elbow with respect to Q is the same as minimizing the KL divergence. So this will help you actually obtain the posterior approximation. Okay, so any questions on this? This is the key part. Okay, so I assume that you now understand essentially the principle of variation inference. How does it apply to basic neural networks, right? So what we are doing here is essentially, this is essentially the objective, right? But we are going to rewrite that in this form. So the reason is still very simple, that you just use the sum, well, log of product equals to sum of logs, right? So okay, right? So we know that P, the joint distribution, is essentially the product of the prior and the likelihood. And then this you have a log, and then this will just break down, right? So this it will break down to Q of log. Okay, and then plus the expectation of the density ratio between your prior and the approximate posterior. And this term is effectively just the minus KL divergence from your approximate posterior to your prior. So this is effectively what we are doing. Okay, so yeah. Okay, so for deep learning practitioners, right? So the way to understand this is to think about two things, right? So the first term here is something we also call it data fitting term. So imagine that you have some loss function, let's say cross entropy or like L2 error, right? So cross entropy corresponds to Bernoulli likelihood. L2 loss corresponds to Gaussian likelihood. So effectively speaking, you are also doing something similar to maximum likelihood here for the data fitting term. And in particular, if you actually don't have the KL regularizer, so imagine that this red term does not exist, you only optimize or you only maximize for the blue term, then this term will actually tries to make your Q distribution going to a delta measure. Basically, it will put all the mass centered around the maximum likelihood solution. In other words, so what we can say here is, if you ignore the KL term, then the solution that you will get from this objective will essentially be the same as maximum likelihood, basically the same as how you train your neural networks, deterministic neural networks. Okay, but what is interesting here is we actually have the second term, which is the KL term, right? So effectively, it just tells you that, okay, so I want to ensure that my Q distribution is not collapsed towards a point estimate, and instead I want it to be somehow regularized in quote, okay, by the prior, okay? So this can be actually quite useful. So you can imagine that you only have, let's say, 3 data points. Okay, so if you do your maximum likelihood fit on 3 data points with a giant neural network, so apparently you can very quickly get overfitting. Okay, so the KL term here basically just tells you that if you use an uninformative prior, let's say Gaussian prior with a mean 0 and some broad variance, then at the beginning you are very uncertain about what the parameters of your neural network should be. And then after seeing 3 data points, because you only see 3 data points, right, then your KL term will still dominate quite a bit. So you should still be uncertain in terms of what the, say, optimal parameters should be for fitting your data. Okay. So yeah, So we've discussed the second part, right? Essentially how you find your Q distribution to fit your posterior, right? So there are a few questions actually about fitting this Q distribution in practice, right? So if you have, let's say, millions of data points, then essentially you cannot put all the data points in the same batch and then run gradient descent, right? So we need to do some kind of mini batch gradient descent or mini batch based optimization. So in this basic neural network literature, people also find out a way to actually make it scalable. Okay, so it also comes from essentially this term. Okay, so the log data term, the log likelihood term here, if you make this conditionally IID assumption, basically says that if you know the neural network parameter, then the prediction for each different data points, they are IID, right? Then you can write your likelihood term here as a sum of individual data likelihood terms. Okay, once you have the sum, right, then we can know that we can estimate the sum of logs, okay, in an unbiased way by taking a mini batch of data points from your data set, and then you calculate the mean of the data likelihood on this mini batch. So this explains why you have this sum and also this denominator m here. But here it's like something slightly different from, let's say, the mathematical training here is you also need this big M factor here. So this is to ensure that you have the right count for the data points, right? So I previously explained that your model should maintain different level of uncertainty when it has only, let's say, 3 observations or 3 data points versus like, say, 10 million data points or even, say, 1 billion data points. Okay, so this n here will actually tell you, okay, if I have a small data set, right, then the KL term will still dominate. If I have a big data set, right, then my data term starts to dominate, and my model should feel more and more confident in terms of, its corresponding fits to the data set. Okay. So this is the first step in terms of the practical implementation to make it scale. So the other thing that people also work out here is automatic differentiation. Well, deep learning people like automatic differentiation. Okay, so because here we need to compute the expectation, and inside the expectation, this log likelihood term involves passing your input x to a very complicated neural network, okay, to get your prediction y. So this highly nonlinear neural network represents a nonlinear function over theta. So this expectation here is intractable. You need to somehow estimate it. So the way to estimate it is, again, via Monte Carlo. So it's kind of like you get the prediction, right? So you sample a bunch of networks weights from your posterior queue and then ensemble the predictions all together. Okay, so the interesting question here is now this theta k becomes random samples from your distribution. How do you actually perform backprop or gradient descent? Okay, so there is this very classical trick, okay, called a reparameterization trick. Okay, so this actually comes from the Variational autoencoder paper, but the actual kind of a trick actually is somewhat exists even before that. Okay, but the idea here is trying to write your random variable as something that is differentiable, okay, in respect to your parameters that you want to optimize. Remember, in the Gaussian case, right? So imagine your Q distribution is a Gaussian distribution with some mean and some variance. The thing that you want to optimize in your variation inference is the mean and the variance. So if you rewrite this sampling procedure, right, then you clearly write down basically the transformation of your random samples theta okay, in terms of its underlying distribution parameter as well as the underlying randomness. Okay, if you clearly write down these two things, the distribution parameter and the underlying randomness, then your automatic differentiation tools will actually figure out, oh, it only needs to differentiate through the parameter part. It does not need to take into account the inherent randomness in this sampling procedure. Okay, so this is the idea of this reparameterization trick. Really write down the sampling process as a function of the underlying distribution parameter and the inherent randomness. Your model will figure out how to differentiate through it. Okay, so you can just plug in this term here, right? So now this entire objective here, it is a function of the parameters that you want to optimize. Okay, you just need to apply automatic differentiation. So you can put all the things together, right? So effectively, what you are doing here is you compute the mini batch data points. Okay, you also sample a bunch of weights from your Q distribution with the previous mentioned reparameterization trick. Okay, and then while the KL divergence, if you use Gaussians, there exists analytic solutions for the KL divergence between two Gaussians. So you can also use these analytic solutions. If not, you can also do Monte Carlo. Okay, so just to say that in regression, as I said, right? So in regression, this is your likelihood, basically the distribution of y given x and theta. So this corresponds to using L2 loss. In classification, the likelihood term is the categorical distribution over y, so it corresponds to the cross entropy loss. Okay, so yeah, so the third step I already mentioned, once you train this Q distribution, then you just in prediction time ensemble a bunch of weights parameters from the distribution, and then you can get the prediction done. Of course, there exist other methods. I only mentioned one. Okay, so I mentioned that you can also use different Q distributions, and Q distribution can go beyond Gaussians. So there exist other methods to get this approximation done, like Laplace method or like moment matching. Moment matching is somewhat related to using the other KL. So there are other approaches based on sampling. And there are also other approaches based on thinking about, okay, I don't want to treat the weights as random variables. Instead, I think about the functions, basically the neural network functions as random variables, and then think about how you can put distributions and optimize distribution around there. Of course, ensemble methods can be framed under Bayesian framework, okay, although there is some debate on that. So, well, I'm going to show you some code. Previously, I thought that I have the notebook, but unfortunately, due to some network issues, I don't have the notebook anymore. But I can show you some code, essentially to tell you that it is actually not super difficult to actually code out all these interesting examples. Okay, so let's see. Okay, so this is actually some code from one of my previous papers. So I just want to show you the difference between how you will code out a normal neural network versus, let's say, this kind of Bayesian neural network. Okay, so it's a little bit complicated because we are building a wrapper that can directly convert any deterministic neural network into a Bayesian one. But the key components are the following. Okay, so first of all, the parameters. So instead of having the weights as the parameters, right? So you can basically see that we have some parameters called weight mean, okay, and something called this underscore weight standard deviation, right? So this is just trying to parameterize the distribution. As I mentioned, we want to use Gaussian distribution for the weights. So similarly, we also have the same kind of parameters for the bias, basic mean, and the standard deviation of the bias. So something, as I mentioned before, right, that we want to ensure that the variance of the distribution is positive. Okay, so this is essentially what we are doing, right? So our actual parameter that we want to optimize is this. Yes. Okay. How does it look now? Okay? Okay, fair enough. Okay, so maybe just to show you again, right? So we are parameterizing the mean and the variance of the weights and biases, not directly the weight and biases. Okay, and in order to ensure that your weight variance is positive, right? So this self dot underscore weights SD is the parameters that you actually optimize. But the thing that you're going to use for variance is you need to actually plug into a nonlinear transformation to ensure that it is a positive. Okay, you do the same thing for the bias. Okay, so now in terms of forward pass, right? So ignore the first part, which is actually another trick that to make it work even better. The standard Monte Carlo approach is the following, right? So you first sample the weights from the Gaussian distribution. Okay, we have this normal sample kind of function here, and the normal sample function is effectively just what I said. This re-permutation trick, right? You get the mean, you get the standard deviation, you sample a random variable, basically standard Gaussian variable, and then you basically compute this output. Okay, so you sample your weights, and also you do the same thing to the bias, and then you put in this kind of forward pass. Okay, this is super thing basically just calls your original neural network functions. Okay, for example, like this n.linear or some other n.conv. Okay, and then this would just plug in the weight and bias to this original neural network function, and then you just do the forward pass. Okay, so you can basically see that it is actually fairly easy, I would say, in terms of calling out this thing. And if you look at essentially how the code itself works, right, at least for this code base, right, so what we've done here is you basically build a neural network from some interesting kind of a template. And then you first, we call it Bayesianize, right, Bayesianize this by putting essentially the particular inference engine, right? So the training time is actually fairly simple, right? So you basically use your neural network to produce the prediction. And in this case, this net.xstring is not doing the deterministic neural network. It is actually doing this forward pass, right? Which basically means you do this Monte Carlo sample procedure as I mentioned before. Okay? And then you compute essentially your cross-entropy loss. That will be your data fitting time. So remember the elbow here, you also have the k alpha, right? So the thing that we written down for each of the layers is its own KL divergence kind of module. So between two Gaussian distributions, there exists analytic solutions. So you just write it down there. And then for each of the, for each of the layers, right? If it is a Bayesian layer, you just first search whether this KL divergence objective exists, and if it exists, you just collect its corresponding KL, okay, right? So ultimately, at the end of the day, you can construct your loss function, okay, in this way, and then you just do the usual backward pass, okay? So really simple, I would say. So in test time, similarly, right, as I said, right, we want to do this kind of ensemble, right? We want to get some samples from the Q distribution. So what we are doing in this code, right, is because in this particular code, every single time that you do the forward pass, it's going to do a new sample of the Gaussian variable. So this is written down in here. So this torch.write line, every single time when you call it, you will sample a different Gaussian distribution. It will sample from a different Gaussian random variable from the same distribution. Okay, so effectively speaking, if you call it k times, it will just give you k different samples, and then you ensemble all the output together, and then you just compute the mean. Okay, so I think what I'm trying to show you here is that the method is actually not that complicated as long as you know where to put in the samples procedure, where to put in the KL divergence, and then you are done. Okay. So I've shown you some kind of basic examples, right? But of course, now the question here is how you can apply these two language models. Okay, so One of the complaint that the deep learning people give to this idea of Bayesian neural network here is, in prediction time, right? You also need to run Monte Carlo, and usually to show the power of this approach, you need to actually take k samples, where k can be some numbers like 5 or 10 or something like that, right? So before people realize that, oh, nowadays language model needs to do test and compute, so people actually don't want to do multiple forward passes for a neural network. So this is the quote that I have heard about it from many practitioners before. So we run a giant language models, k sample Monte Carlo is too slow. Okay, so the interesting question here is, can we actually address this problem somehow, right? So I would say it's actually quite challenging, to be honest, right? Especially for the people who develop these Bayesian networks, they mostly come from the statistics and probabilistic machine learning community that we didn't think too much about this engineering approaches, especially writing CUDA kernels. Okay, but there is one way that you can address the problem. So I believe that most of us in the room has no big GPUs to actually do the pre-training, right? But you may want to compute something for fine-tuning, right? And in fine-tuning approach, right now, one of the popular paradigm here is called low-rank fine-tuning. So the idea here is the following, right? So you don't actually want to fine-tune the entire weight matrix within your layer. Instead, what you're going to do is you're going to compute your new weight matrix as your old weight matrix, basically your pre-trained weight matrix, plus essentially a matrix constructed by some low-rank matrices. Is that? Maybe I should actually give you a break, okay? Yeah, maybe let me just finish this part and then we can go for a break. Yeah, as visualized here, right? If AB matrices are low rank, then effectively speaking, you actually don't need to fine tune or train many parameters as compared with training for pre-training for a big language model. Okay, so this effectively reduces the parameter counts for the Bayesian methods that we need to do in fine-tuning time. So what I'm saying here is that it is not like directly addressing the complaint that previously language model people have, but it's kind of like doing a smart cheating approach. You are not addressing the core issues, but you are making these problems smaller. Okay, so let's see how it works, right? So so this idea of applying Bayesian methods to LoRa has been around for maybe, I think, 3 years right now. So the state-of-the-art approach right now is actually at this year's ICML, basically last week, okay, in Seoul. So effectively, they try to apply their Bayesian fine-tuning approach to open source language models, including essentially Qwen3 30 billion parameters. Okay, on these downstream tasks, including math reasoning problems. So at least it shows to you that it can work, right? And okay, right? And compare with other approaches, it gets some slight advantages. Well, of course, it depends on how you choose your parameters. So the other questions that people care about is the speed, right? And also the memory consumption. So in terms of the parameters that you need to train, it's actually quite close to the original LoRa method. Okay, so basically like 4.5 million versus 4.9 million. Okay, I think the difference is negligible. So the speed side, of course, it is still a bit of a problem, but at least this approach is already much faster than other kind of Bayesian approaches. So all these approaches, apart from this map one, is the previous Bayesian version of the LoRa approaches. So this one actually provides you quite good improvement, of course, because they also spend time writing some low-level code. Okay. So my student also tried something similar, but in a different domain. So this is essentially chemistry language models. Okay, so in chemistry domain, people are also interested in pre-training on basically a big corpus of molecules and then see whether they can be translated for downstream task use. And for downstream task use, you also want to fine-tune your neural networks, right, for those downstream tasks. So, I mean, the story for this result basically just tells you that, okay, fine-tuning does work, right? And it actually gives you better kind of performance in terms of root mean square error for this prediction task. And in terms of some calibration metric for ECE, it also gives you basically better calibration, so lower is better. So I think we can give a break, but I just want to mention that I mentioned one kind of word, calibration. And calibration is actually one of the very important concepts in terms of evaluating uncertainty quantities in neural networks. So I think we can take maybe 10 minutes break. So while people are coming back, I just want to say that I've been told that I need to skip some parts, right, because of some issues, right? But it's okay, right? Because you know, I do things more on the Bayesian side. I mean, I don't hate frequencies, people, but I just want to show you one image, right? That if some of you in the audience is like preferring frequencies statistics, right? Where you know I mostly do Bayesian statistics. Something that maybe you want to have envision here is that frequencies statistics basically work on this problem of random variable y condition on random variable x, which means both of the input and output that they are random. Okay, and the statistics, Bayesian people, when they want to say some kind of interesting result, they treat the input x as a given variable, so it is not random. You only look into basically the conditional distribution of y given a particular x. Most of the calibration guarantees that people will get for uncertainty quantification is based on this joint distribution case where it is only called marginal guarantees. It is not the usual thing that you are expecting. If you are interested in this, then we can definitely chat offline. But I unfortunately need to go to the third part, which is, I think, maybe more exciting. Okay, so we talk about language model as the starting point, right, for motivation. And I told you a bit about how we can compute these Bayesian neural networks. Unfortunately, I don't have time to tell you the calibration, but at least this part uncertainty in context learning, we are not showing calibration as an example, so that seems to be okay. But what is in context learning? Okay, so well, this ChatGPT answer is like already like maybe 2 years old, because I asked with ChatGPT 2 years before about this question, right? But effectively, what it says is, in context learning is a phenomenon observed in language models where the model can adapt to a new task simply by being provided with examples or instructions within the prompt without actually changing any of the underlying parameters. So it is not pre-training, it is not fine-tuning. Okay, so but how would you actually use, let's say, in context learning to do some kind of machine learning task, for example, like supervised learning? Okay, effectively speaking, right, nowadays you interact with language models by putting in some tags, arbitrary length of tags, and then it will produce you some output, right? But equation-wise speaking, a language model actually defines a set of conditional distributions. So it can take arbitrary length of the input tokens and then produce you next token prediction. So this is essentially how an autoregressive language model works. Okay, so now imagine you want to adapt this to a supervised learning task, where it can be a regression problem. So in a regression problem, your x will be your input covariate, and then y will be your output kind of values or labels. Okay, what you can imagine here is you can put sort of like the odd tokens as your input, x, and then an even token as your output, y. Okay, then it means that the prediction that you're interested in, right, which means I want to produce the prediction for x star, my test input, given all my previous data points, is you're going to put in 2n plus 1 tokens. Okay, the first 2n tokens will be these x1, y1, x2, y2, and okay, until x n to n, x and yn, and then you can use x star as your 2n plus 1 token, and you hope that your 2n plus 2 token will be your prediction of y star. So this is the setup. But of course, the actual prompting won't be that simple. Okay, we are just trying to use this as sort of like the mathematical framework to think about the problem. But the actual way to do this is you need to design some kind of a prompting template. Okay, I'm sure that you are better than me in terms of designing your prompt template, but at least in this example, what you can do is to, for example, make this kind of formatting, right? Saying that you have some kind of input here, this is 2D, right? So each of dimensions has this value, and then you want to classify this particular point in terms of one of the classes. So we actually prompted this in this way to the Quen 2.5 14 billion models for these 3 spiral kind of classification problems, and this just gives you the classification probability output. Okay, so at that time we were amazed that it somehow actually works. Okay, maybe this time, so you shouldn't be too amazed by this. Okay, so the interesting thing that we can say here is how does that actually relate to what we talk about today in terms of uncertainty, right? So there is one classical result almost 100 years ago, okay, from an Italian statistician called Bruno Definiti. Okay, so here's the result. If, for example, you construct essentially the prediction for all of your inputs, okay, basically your inputs x1 to xn, right? You construct all the prediction y1 to yn. If the prediction result, distribution speaking, remains the same when you permute your data set in an arbitrary way, right? So then the Definiti's theorem indicates that there exists an underlying Bayesian model that tells you your model actually predicts things according to this. Okay, so I don't have time to actually tell you the proof of this result because it's actually very, very involved. Okay, but what I'm trying to say here is if your language model actually satisfies something called exchangeability, which is what I mentioned, right? Permuting your inputs does not change your result, then your model is actually doing Bayesian inference. Okay, so this sounds quite nice, and it's actually the basis of basically tens of years of Bayesian statistics work, because this exchangeability or going to existence of Bayesian model result tells you instead of constructing a giant model for this joint distribution, I can just go for the Bayesian modeling paradigm, right, the explicit one. I just put some prior, I just design a likelihood, and then I just need to figure out how to compute the posterior. And in the first part of the talk, we already tell you how to approximate the posterior. We already have methods to do that, right? So that is actually quite nice, right? But nowadays, language models advances actually allows us to specify this big joint distribution, and they are very, very powerful. Okay, so it is actually interesting to rethink this paradigm of going directly for the big joint, the big prediction distribution, and then see whether you can get some interesting behavior in a Bayesian sense from it. So putting that in this way, right? So in the previous approach that I mentioned, including Bayesian neural networks, right? You are doing this thing called explicit Bayesian modeling. You put some prior over the model weights, okay? And then you essentially build out your likelihood, okay? In the implicit or predictive Bayesian inference case, it's actually closer to what I mentioned about the language case, right? So you build a model directly for your entire data set, okay? And you actually want to build that for essentially your entire data stream, okay? So some people might be interested in also this term, which is actually really somewhat similar to these post hoc explanations in explainable AI. But today I'm not interested in this term. I'm purely interested in this kind of big predictive model and see whether we can address this following question. So as I mentioned, right, so the definitive theorem actually provides the motivation for Bayesian statistics to work on the explicit Bayesian modeling paradigm for tens of years. Now we have this new kind of a big predictive engine. Can we still simulate some kind of a Bayesian algorithm, okay, on this new paradigm, or the renewed paradigm? So the answer is potentially yes. I'm going to give you 2 examples. Okay, so now I should mention a bit about uncertainty, of course, right? So the reason that we do Bayesian inference is not only about doing this kind of prediction via ensemble, but we also want to understand, whether we can put some uncertainty quantification or uncertainty metrics over the output of our predictions. Okay, and in particular, we are interested in this interesting kind of way of specifying uncertainty. So we have this interesting kind of expression in quote. Okay, total uncertainty equals to epistemic uncertainty plus aleatoric uncertainty. So let's explain each of the terms in detail. So now imagine that you are in the experiment of flipping a coin, okay? And you may want to understand whether the coin is a fair coin or is a bent coin. And in particular, you want to know essentially the probability of this coin flip being basically upwards, okay, or heads or tails, right? Okay, so this is the estimation problem of estimating the underlying probability of heads given only observing a few coin flips, okay? So of course, you can construct some estimators of the underlying probability, right? But you might not be certain about your estimate. If, for example, I only show you 3 coin flips, okay, maybe let's say 2 heads and 1 tails, right? So your imperial estimate will be saying that the probability of going to heads will be like 2/3, right? But you only have 3 coin flip examples. In this case, we are not certain about whether this 2/3 probability of going heads is correct. Right, so this represents what we call epistemic uncertainty, the uncertainty coming from the lack of data. So I can continue showing you the same coin flip results for many, many times, let's say 300 or 3,000 times, right? So we have more and more data points. I can get these estimates of the mean probability of heads, right, adjusted based on my data set. And because I have more and more data points, I will become more and more certain about it. So epistemic uncertainty reduces when we have more data. However, even when I give you infinite number of observations for this particular coin flip, right, so that you are absolutely certain about the mean probability for this coin being being heads, let's say 2/3, right? I can still ask you the question about, okay, what is the outcome of the next coin flip, right? So coin flip itself is a random event. Okay, even when I know the underlying probability, I still don't know the exact outcome of the random event. Okay, so that part is something called aleatory uncertainty. So what is the next coin flip's outcome? So it is non-reducible even when you have infinite amount of data. So this basically says when you estimate uncertainty, right? So you actually want to understand the source of uncertainty. Where does it come from? How can you reduce it? Some of them cannot be reduced. If they cannot be reduced, should I actually exclude them in my algorithms? Okay. So this is the concept. How would you actually compute it, right? So there are different metrics, right? So we are talking about 2 types of metrics. So the first one is essentially entropic-based metrics or something related to these information theoretic approaches of doing uncertainty quantification. So if you think about in classification, for example, you have a 10-class classification, then computing the entropy is simply just to compute essentially this P log P for each of the classes, and then you sum over all of them, and then put the minus sum. So this is just the definition. So a visualization to tell you about this entropic metric is the following, right? So if you have a high entropy in this discrete case, right, in fact, then your distribution is relatively flat across all possible classes. So that in this case, you shouldn't be certain about your prediction case, okay? So, but if you have a low entropy, and in fact, if your entropy tends to 0, right, then effectively speaking, in this discrete case, your distribution will have a big mass only on one class. Okay, so this also reflects that, okay, when I have a small entropy, I probably should be quite certain in terms of the prediction result. Okay, so this is why entropy can be used as a metric for uncertainty quantification. So we previously mentioned about this total uncertainty decomposition approach. How does that translate, okay, to the Bayesian version? So let's just recap, right? So we mentioned that If you have a Bayesian model, explicit Bayesian model, then what you can do here is you can build a posterior or approximate posterior, right? And then this is how you actually do the prediction. You're going to ensemble all the possible answers from your posterior, right, to get your final prediction. Now, you can of course compute the entropy for this distribution as your uncertainty measure, right? But in this case, it is only representing the total uncertainty. We can further decompose this entropy into two terms. So we mentioned epistemic and aleatorial uncertainty. So the aleatorial uncertainty here is, effectively speaking, you take each of the members in your posterior, you compute its own uncertainty, basically entropy, right, given a particular parameter theta, and then you average over all possible aspects in your posterior. So this is something called aleatorial uncertainty. Okay, and then via decomposition, you just basically subtract the aleatorial uncertainty from the total uncertainty. Then this will give back to the epistemic uncertainties, and it turns out to be the mutual information. Okay, so why do we actually do this kind of decomposition, right? So let's just try to see what does aleatorial uncertainty mean, right? In the motivation of the coin flip example, I tell you that this is the uncertainty that is inherent to your data, right? So it is the inherent randomness in the data so that it is irreducible. Now, assume that you believe your model is correct, which basically means that there is an underlying parameter theta star that agrees with your data generating distribution, okay, right? Then effectively speaking, if you know theta star, then you can compute all different kind of uncertainty measure on this distribution parameterized by Q star. And in particular, for example, if you use entropy, right, then it is effectively just the entropy of your distribution P of Y star given X star and your ground truth parameter theta star. Okay, so this represents essentially the true aleatorial uncertainty for your data set. But of course, the problem here is that you actually don't know theta star, right? You can only estimate theta star from your data set. And you only have a finite number of data points. You actually don't have infinite number of data points. You actually don't know whether your estimate of the theta is actually the corresponding ground truth theta star. What can we do, right? So let's just do a Bayesian estimate of this, say, degree of randomness, right? So we are basically saying that, okay, let's pick the parameters theta from all of the posterior samples. Okay, for each of the members, I'm going to pretend that the theta is the ground truth and compute its corresponding uncertainty metric. But theta is not the ground truth, right? I'm just going to get a bunch of different guesses from my posterior and average of it. In particular, again, if you believe in your model and under some regularity conditions, then when you have an infinite amount of data points, your posterior distribution here, P of theta given D, will actually converge to the delta distribution around theta star. So basically it just tells you that when data goes to infinity, your model actually converges to the true answer, so that your Bayesian estimate of the aleatorial uncertainty also converges to the true aleatorial uncertainty. Okay, so this is why we do this kind of estimates. And the epistemic one is basically just by the additive decomposition rule. But because entropy minus the conditional entropy is just mutual information, and we can also exploit the interpretation of mutual information here. So the first interpretation here is something called expected information gain. Okay, so by definition, you can write mutual information as the expectation of some k-out divergence. You can write in two ways. One is the k-out divergence from the updated posterior to the original posterior. Updated means that you add in one more data point. And just notice that here, this Y star is not your ground truth. Y star is actually coming from your model prediction. Okay, so what does it mean? It just tries to compute essentially the difference of your posterior after seeing one more data point. Okay, if your data point is somewhat new comparing to some previous data points, right? Then your updated posterior should look quite different comparing to like the original posterior, so that this term will become big. Okay, so this is one of the interpretation for this epistemological uncertainty. Okay, that you can use that for many of the interesting tasks like active learning and reinforcement learning. But there's another interpretation because mutual information is symmetric. You can also write mutual information as the expected KL, but now you look into Y star as your random variable. So you're writing this as the KL divergence from a single model's prediction to an ensemble of model prediction. So effectively speaking, if your KL divergence is big, right, then it just tells you that this single member in expectation does not agree with your full community, right? So disagreement is high. So when you have a high disagreement, then it signals uncertainty in terms of your prediction. So people actually use these kind of ideas in, for example, like auto distribution detection and various kind of other detection tasks. Okay, so this is mutual information, but of course you can also do variance as well. Variance is another metric for uncertainty, and there exists similar kind of decomposition as well. So via this law of total variance, so variance equals to essentially the expectation of the conditional variance plus the variance of the conditional expectation. So that's the also a similar decomposition rule. Okay, so hopefully at this moment, you've seen kind of some motivation about why we are interested in doing this decomposition, but the question here is how we actually do that in the language model setup, right? So remember that we said that language model, if you make sure that it satisfies these exchangeability conditions, then it is actually doing Bayesian inference. But it just tells you that there exists an underlying Bayesian model, right? You actually don't know what the underlying Bayesian model is. Okay, so in fact, you actually don't know what theta is. Okay, so this tells you that while this equation, okay, for this decomposition rule still hold from equation perspective, because you actually don't know what theta is, you cannot compute it directly. So just to say here, in the language model setup, right, now theta is different from the previous part of the lecture, right? So previous part of lecture, we use explicit Bayesian modeling where we view theta as the neural network weight. In this case, for the in-context learning setup, I would recommend you to think about theta as some kind of latent knowledge, somewhat implicit in your language model. You know it exists, but you cannot tell the form of it. So it is really the unknown thing that we signal at the very beginning. Okay. So the question here is, now given that we just know some knowledge exists, but it's unknown, we still want to do something by exploiting its kind of this previous results on the decomposition. So how can we do that? So the answer is you can do that approximately. Okay. So here's what we are going to do. Okay. So before you actually ask the language model the real question, basically X star is your real question, you're going to pick an auxiliary question, or we call it probing question, Z, okay? And then you ask the language model to actually provide the answer, U, for this probing question Z with the context D. So language model is actually can produce predictions for arbitrary length of input, right? So which basically means you can indeed compute P of U given Z and D, okay? So once you get the language model's answer U to your auxiliary question, you're going to append both the probing question Z as well as the answer U to the context again, and then ask the real question. So this is computing the P of Y star given X star and U and Z and D. This is inside term. So again, language model can produce this prediction for arbitrary length context, so you can absolutely do it. So of course, right, so these are all kind of expectation entropy expressions. You need to do multi-color estimates, but trust me that we can actually compute this term, or we can estimate this term in a multi-color way. So what we are saying here is that we can show this procedure of, let's say, asking an auxiliary question first and then ask the real question later, gives you a upper bound to the aleatoric uncertainty that you want to estimate if you actually know the underlying latent knowledge of your language model. Okay, and this is actually true for any auxiliary question that you can ask. And we know exactly the gap between your upper bound and the editorial uncertainty that you want to estimate. Okay, so bear with me, right? That I just said that this is true for any auxiliary question Z. The things that variational inference people like to do is once you have a bound, you just optimize the bound to get the best bound, right? So you have the upper bound to the editorial uncertainty. You just minimize the upper bound, which means we are going to optimize the probing question that we are going to ask for the language model. Once you find out the optimal question, right, then you get this estimate of the editorial uncertainty. You can use the additive rule, total equals to epistemic plus aleatoric, and then you can compute the epistemic uncertainty as well. So here, because you have a upper bound for the aleatoric uncertainty, then you will have a lower bound to the epistemic uncertainty. Okay, so this looks like magic, okay, but it is actually not magic. The reason why this works is actually super simple. So if you have ever taken any courses related to information theory, data processing inequality is the 101 thing that your lecturer will tell you. So here's the idea. So remember, right, that the epistemic uncertainty in this information theory definition is the mutual information between your prediction y star as well as your latent knowledge theta. Okay. Now, if you think about how this Bayesian model works, right, then effectively it tells you that whenever you answer a question, either the real question or the auxiliary question, your model needs to use its own latent knowledge to answer you, right? It basically just says that your model needs to go through the latent parameter theta to produce the answer. So this means you can think about these auxiliary questions answers U as a noisy measurement of your underlying latent knowledge. Okay, right? It's fairly intuitive. I mean, if you ask me questions, for example, regarding, say, some kind of frequency statistics and answer you, right? You can basically base on that to evaluate whether I'm expert in frequency statistics or not, right? So this is basically the same intuition. Now, if you have you as your noisy measurement of your underlying latent knowledge, then what we actually compute previously for this epistemic uncertainty, when you use this entropy minus this estimation, and this estimation here is also the conditional entropy. Effectively speaking, our variational lower bound for the epistemic uncertainty is actually the mutual information between y star and your noisy measurement of the latent knowledge theta. And by data processing inequality, it just naturally gives you a lower bound. Okay. So of course, the question here is, U is a noisy measurement of theta, right? But different kinds of noisy measurement will reveal different amount of information. So that's basically why we advocate for optimizing Z, right? If you ask a good question, then you will reveal a lot about the model's knowledge. Okay, so this seems nice in theory, right? But the proof and the grounding here relies on a fact that the model is really doing Bayesian inference on the line. Okay, the question here is, do LMs really do Bayesian inference? Okay, so I think this has been debated quite a lot in the field, either from the theoretical perspective or from practical perspective. But I would say that I don't think language model, if you prompt it simply, is doing Bayesian inference. Okay, because this exchangeability thing is actually very difficult to satisfy, right? Exchangeability tells you that, if you permute your input questions in all possible ways, the distribution of the output should be the same, right? But if you think about your own experience of prompting language models, right, then this is obviously not true, okay? So now the problem here becomes, okay, so you've got some nice theory results, but it does not agree with practice. What do you do, right? So what we are doing here is we start to construct process of prompting language models to make it approximately speaking exchangeable. So think about a few different conditions, right? So first, You want to ensure that when you permute your input, okay, the output becomes the same, right? So what we can do here is we just simulate the permutation, and then we ensemble the output from the permutation. Okay, so this is the way to address this permutation invariance. But exchangeability is not only about permutation invariance. It is also about something called martingale property. So how to read that? So it basically just tells you that, okay, because you just ask a language model a question, right? A probing question Z, you actually don't tell the language model what is the ground truth answer of the probing question Z. So it means that your language model has learned nothing new or nothing new in terms of real information from your probing question. Okay, since your language model hasn't learned anything new, your language model should produce the same answer on average to your real question, okay, as if you were to just directly ask your language model the question. Simply put, right, your probing question should not add any new information to the language modeling procedure. Otherwise, the previous kind of intuition about this noisy measurement of the underlying knowledge does not hold. So the way we do that is to restrict the search space of these questions, and then we filter out the questions that does not satisfy this martingale property. So let's just put in this kind of procedure in a look, right? So the prompting procedure looks like this. You pick a set of auxiliary questions Z. You perform the previous procedure that I mentioned, right? Just asking the auxiliary question, get the answers, and then compute the real answers, compute all this distribution thing, okay? And then we filter out essentially the questions that do not satisfy the martingale property, and then within the remaining questions, we find out the ones that has the minimum estimate for the aleatoric uncertainty. So how to choose these Z candidates, right? So you can definitely ask random questions. You can also, for example, like perturb the ask similar questions. So if your X is in a real domain, like classification or regression, right, then you can define some kind of epsilon ball within your X star and then ask questions within that. Or you can even repeat the questions that we somehow also find it works in practice. Okay, so this is just to remind you that these are our prompt templates. This is really how we prompt language models. Okay, the things that are different from previous example is basically we just ask more questions based on this appending Z and U into the context. So yeah, so this is essentially the previous example, right? I already showed you that how you can prompt the Quant 2.5 14 billion models to do this 3-class classification. Okay, you can use this approach to compute the uncertainty decomposition. So the total uncertainty is visualized in this way, right? But then if you look into the decomposition that we actually computed with our method, then you can essentially see that it highlights different regions. So the aleatoric uncertainty here is somewhat high around the boundary of the classification of the class, right? So when your data point is at a boundary, then you are naturally uncertain. This is especially coming from your data properties. So this is aleatoric. But then if you look into the epistemic one, right? So it is higher around these regions where you have a low amount of data. So again, this reflects the idea that epistemic uncertainty represents the lack of knowledge due to the lack of data. So you can do similar things for regression. Okay, so this is a 1D regression example where we typically kind of simulate these data points in a way that here you actually have lower amount of noise in your data distribution, and here you actually have a higher amount of noise in your data distribution, which means that the aleatoric uncertainty in this region is higher than the aleatoric uncertainty in this region. So if you use our decomposition approach, right, what you can see here is, so first just to say that this blue curve represents the total uncertainty and the pink curve represents the aleatoric one. So you can see the aleatoric uncertainty here in this region, basically this region of high noise, is higher than this region of low noise. And second, in these gap regions where you don't observe data points, okay, you still see this kind of increase of the gap between the blue curve and the pink curve, which signals the increase of epistemic uncertainty. Okay, at least visually speaking, it works, right? Unfortunately, we don't have a way to quantify whether it is calibrated. I haven't mentioned the concept of calibration today, but yeah, it is definitely a problem. You can also do that for language models, right? So at the beginning, I mentioned about this language model as an example. So what you can do here, so this is a simple example. It is a QA data set that I think the answer is basically just binary, okay? So you can use this idea of abstention in question answering, right? So if your language model becomes uncertain up to some threshold, then you can say, okay, language model can decline for answering. Okay, so in this case, you actually need to think about what kind of uncertainty you are going to use for this abstention procedure. We can use either total uncertainty or like epistemic uncertainty or like aleatory uncertainty. So in this case, we tested out essentially both total uncertainty and also aleatory uncertainty. Okay, and aleatory uncertainty is computed using our estimation procedure. So I will first say that first, after filtering out the uncertain kind of answers, the accuracy of the remaining kind of being answered questions become higher. So this is as expected, but you can also see that using different kind of uncertainty actually gives you different results in terms of this abstention or in QA accuracy performance. So in the interest of time, maybe I will just also mention a bit about some other applications beyond just classification and also, let's say, predicting some uncertainty values. And this is actually something that is more interesting in the sequential data, so sequential decision making and also reinforcement learning setup. Okay, so I'm going to talk about multi-arm and bandit. So suppose you go to a game arcade center, okay, and you want to pick a machine that gives you the highest reward on average, but because you're only new to the game arcade center, you actually don't know which machine is the best machine to play. You want to collect some data, right? But playing each machine means you need to pay some money, right? So you also don't want to collect too much data, okay? So this is a typical multi-arm bandit setup. So you want to choose a machine or basically choose an action that can maximize the expected reward, but you don't know the ground truth. You actually don't know which machine has the highest reward. You need to find out a way to estimate it. Okay, so here's a classical algorithm for addressing this task. Okay, so this is a model-based approach called upper confidence bound. So it means that you need to maintain an estimate for the mean reward for each of the machines. Okay, but then because you don't know the machines, right? You're going to collect data, and when you collect data, you only have finite amount of data. You do have some uncertainty. Okay, so UCB says you are going to select an action based on this interesting acquisition function that balances between your current reward estimate and also some uncertainty measure, right? It just tells you that, okay, if my uncertainty is high, right, then I might want to play with this machine more because I want to collect more data, right? And also if my estimated reward for this machine is high, and because I want to maximize the average reward, I also want to play this machine more. So there is this interesting balance. So once you select a machine to play or select an action, you just play the machine and then it will return you a reward. And then you need to use these new data points to update your estimate for the reward for these machines. Okay, so the hope here is when you continue play more and more, right? You collect more and more data points, then you will become more and more confident in terms of your estimate for the mean reward for each of the machines, so that your sigma, right, reduces to 0. okay? And your estimate of the mean reward goes to the accurate one so that you know which machine to pick. Okay, so it actually depends on how you estimate this uncertainty. And as I mentioned before, right, you can also use a variance as the uncertainty estimation quantity, and this kind of decomposition idea also works out. You can also ask a auxiliary question, and then based on that to estimate this conditional variance, and then this will also give you an upper bound to the aleatory uncertainty in the variance form. You can also get this uncertainty estimate here. Yes, okay. So we are basically using this approach in the UCB algorithm. Okay, so effectively it's the same as I mentioned before, except that you're just going to use this estimated epistemic uncertainty or epistemic variance as your sigma square. You just plug in that to your UCB algorithm. Okay, so something that is also interesting here is there is no longer a explicit update for your model, because in-context learning does not update your parameters. You just put in the observed context, observed rewards to your context, and then it will just produce the next prediction. So let's look at this task. Okay, so this is actually a very simple task. So it is a task that is proposed by this nearest 2024 paper. Okay, so it says it has 5 buttons. There is one button with averagely speaking higher mean reward, p plus 0.1. The other arms, they have a lower mean reward. But then you can change this p value to actually make the optimal arm to have a smaller aleatory variance. Okay, so this is the way to actually show you that it is depending on how the underlying data diffusion look like, you might want to use different kind of variance estimate. So just to say this, right? So the way to evaluate the performance is something called total regret, which basically says if I keep on playing this multi-arm bandit game a lot of times, right, whether my model will converge to only keep playing the optimal arm, or it will still somewhat play some other suboptimal arm. Okay, so this is something measured by total regret. The lower the better. Okay, so here's the result that we perform in this prompting experiment. As I mentioned, right, if you set this p in this environment in a different way, then they will have different aleatory uncertainty across the different arms. So when the aleatory uncertainty is lower for the optimal arm, you actually prefer using the epistemic variance, because if you only use the aleatory variance or use total variance, right, when you get infinite amount of observations, which means EV goes to 0, then the aleatory variance for your suboptimal arm will be higher than the optimal arm, so that your objective function might potentially prefer choosing the suboptimal arm. Okay, so we can show you here that in these setups that you actually want to make sure that you have to use the right uncertainty estimate for the task. Okay, so I think the takeaway from this walk is essentially saying that, okay, so we show you that language models, if you think about it as implicit or predictive Bayesian modeling approaches, can be interesting to think about, right? Especially you can think about applying or adapting existing Bayesian modeling techniques in the explicit Bayesian paradigm into this language domain, and then I show you some of the examples that you can perform, okay, in the language domain. So there has been quite some ongoing work that I don't have time to discuss today, but those are from my PhD students. So yeah, so that's it for today, right? So unfortunately, I cannot discuss this frequentist approach here. If you're interested, we can definitely talk about it. But yeah, so lastly, I would just say thank you, and maybe we have time for a few questions.
Excuse me, can we go back to the results of your method? And there was like a difference between the performance of the aleatoric uncertainty and the total uncertainty. I think aleatoric was higher. Just not this one, but the previous one. And I'm trying to understand. Yeah, exactly. Abstention in QA. So why do you think using only aleatoric uncertainty gives you better results? Because I would assume that like total uncertainty should be better.
Okay. Yes. Okay. So, okay. Um, I think it's an interesting question, right? So the um, we have looked into some examples where these two different methods actually give a different verdict, right? So there exist examples where the total uncertainty does not reject, but the aleatoric uncertainty approach do reject them. Okay, so those examples contain some kind of ambiguity. Okay, in the way to understand some words in the question. Okay, so that's our empirical observation. So if you ask me about, what's the difference between aleatory and total, right? It's basically just adding this epistemic part, and whether this epistemic part is somewhat convoluting the results. That's the things that we are not exactly sure.
Maybe it will be the next.
Yeah, definitely thank you for the lecture. I'm quite familiar with the topic of the multi-armed bandits. Maybe you can clarify the differences, like in terms of methods when we use like UCB plus VUED and Thompson sampling. Like before this, I believe that Thompson sampling has stronger Bayesian guarantees than UCB and UVD. Thank you.
Yeah, of course. I actually have some slides about Thompson sampling, but I don't have time to talk about it, right? So the issue here is Thompson sampling, right, requires you to actually sample from the posterior explicitly. Okay, so this is actually the Thompson sampling approach, right? I think you're probably familiar with. Okay, but in the current setup, right, we are just saying that this theta here is the underlying knowledge from your language model. It exists, but you actually don't know how to evaluate it. You cannot sample from it. We are using this kind of probing approach, or like repeatedly asking new questions, or like this predictive resampling approach to somewhat review the information about theta. But of course, you can only review part of information. You cannot review all of them. So this actually results in the gap. In fact, we actually have some kind of similar algorithms similar to the one that I talked about before, that basically says you ask a bunch of questions, okay, to get this kind of imaginary reward from your prediction, and then you, based on that, compute some estimate of your mean reward. But the problem is basically, as I said, mentioned before, right? So because it is only reviewing partial information, you can actually show that this kind of approach results in suboptimal kind of average regret. Okay, as compared with Thompson sampling, this is a thing that we definitely need to acknowledge. That there is no doubts about that. But interestingly enough, in the actual experiment, maybe I can show you this one. Maybe it's better. In the actual experiment, this kind of asking for this imaginary reward actually still works. Okay, I think there are some empirical results showing that sometimes Thompson sampling can be sort of like too conservative or like explore too much empirically.
Yeah, thank you.
Okay. The next question.
Actually, Alexei wanted to ask a question. Maybe he's.
Ah, I thought you were showing how to a question.
Okay, thank you for your talk. A good one. About Thompson sampling, can we provide some theoretical guarantees for some variant of sampling that can say that it will be kind of optimal balance between exploration and exploitation. Maybe like Thompson sampling with temperature, or maybe something more complex.
Well, okay, so I think it depends on what kind of algorithms you're talking about, right? So if you're talking about Thompson sampling-like algorithms, right, we already know in theory that under some assumptions about, let's say, your model is correct or whatever, right? So Thompson sampling is optimal. Okay, so anything that approximates the posterior but still with error will become suboptimal. So this is a thing that is known. So it is no different in our approach. But if you're using some other approaches like UCB, okay, I think something that I haven't mentioned here, but internally we have figured out some ways to estimate the posterior variance in a unbiased way, although it has a very high variance. Okay, so if you think about in that way, right? So it is possible to construct algorithms in this predictive Bayesian inference paradigm to somehow, mimic UCB in a more accurate way.
Okay, thank you. I think we should wrap up, unfortunately. If you still have questions for the lecturer, you can, I suppose, approach here, like after the lecture. Good luck. We now have a short break, like 5 minutes.